Today, we're diving deep inside the atom to crack one of the fundamental codes of chemistry. We're talking about quantum numbers, which are basically a unique address for every single electron in the universe. So let's get right into it.
Here's our plan. We'll start by figuring out why we even need an address system for electrons. Then we'll break down each of the 4 quantum numbers that make up that address. And finally, we'll look at the rules that tell us how electrons actually fill these addresses.
So, first up, let's wrap our heads around the problem of actually finding an electron. Turns out it's not nearly as simple as you might think.
Let's try an analogy, because it really helps. Imagine an atom is this huge, bustling city. How in the world do we find one specific resident, a single electron? The old models of the atom, well, they just weren't going to cut it.
You see, the old idea was something called an orbit. You've probably seen the pictures. It's a neat, predictable path, like a planet circling the sun. But quantum mechanics showed us the reality is way cooler. And it's called an orbital. It's not a path, it's a 3D region of space, like a cloud of probability, where there's a greater than 90% chance of finding the electron. So we're not looking for a dot on a map, we're looking for the neighborhood where the electron lives. So, how do we describe an electron's location inside this probability cloud? Well, the solution is just beautiful. A set of 4 quantum numbers. And together, they give us all the information we need, acting as a one-of-a-kind address for any electron in an atom. Okay, let's break down that address, piece by piece. First up is the principal quantum number, which we just call n. Think of this as the biggest part of the address. It tells us which city the electron lives in.
Simply put, n tells us the main energy level, or shell, of the electron. And a really easy way to think about it is this. A higher n value means a bigger, more energetic city that's located farther away from the center of town, which in our atom is the nucleus.
And the values for n are super simple, just positive integers, 1, 2, 3, and so on. Sometimes chemists call these the K, L, and M shells. But here's the real takeaway. The bigger the number, the more energy that electron has, and the farther, on average, it is from the nucleus. This gives you a nice visual, right? It's like the atom has these nested energy shells, almost like the layers of an onion. When an electron moves to an outer shell, to a higher n value, its world literally gets bigger and more energetic. Okay, on to the next part of our address. We found the city, which is Penn. Now we need to find the specific neighborhood. And to do that, we need to know its shape. And that is the job of the azimuthal quantum number L. You see, inside each energy shell, our city, there are one or more subshells, or neighborhoods. L tells us the specific 3D shape of that neighborhood. Now, the values L can have actually depend on n. It can be any whole number from 0 all the way up to n-1. And each value of L corresponds to a different shape, which we give letters to. S for sphere, P for a dumbbell shape, and D and F for even more complex shapes. And these shapes, they are so important because they're what determine how atoms can connect to form molecules. Let's start with the simplest one. When L is 0, we get an s orbital. It's a perfect sphere. That means the electron has an equal chance of being found in any direction from the nucleus, as long as it's on that sphere. But when L equals 1, things get more interesting. We get p orbitals, and these have a totally different, 2-lobed dumbbell shape. But notice, there isn't just one. There are 3 of them, and each one is pointed along a different axis in space, the x, y, and z axes. This brings us perfectly to our third number. So we know the city, n, and the shape of the neighborhood, L. But which of those 3 dumbbell-shaped houses are we talking about? For that, we need the street address. This is where the magnetic quantum number ml comes in. This number tells us the specific orientation of a particular orbital in 3D space. It's how we tell the difference between orbitals that have the same shape but are just pointed in different directions. So here's the rule. ml can be any integer from -L all the way to positive L, including 0. So think about it. For an s orbital, where L is 0, ml can only be 0. That's why there's only one s orbital per energy level. But for p orbitals where L is 1, ml can be -1, 0, or +1, 3 values, which means 3 distinct orbitals, exactly what we just saw. Okay, we've almost got it.
We have the complete location, the city, the neighborhood shape, and the specific street address. We've found the house. Our last quantum number tells us something about the resident inside, the electron itself.
And this is the spin quantum number, ms. It describes a property that's just built into the electron, like its charge or its mass. The easiest way to picture it is to imagine the electron is spinning on its own axis, which creates a tiny little magnetic field.
And just like a spinning top, it really can only spin in one of two ways. We call these spin up and spin down, and we give them the simple values of positive 1/2 and negative 1/2. That's it. Every single electron is either spinning up or spinning down.
So there you have it, the complete 4-part address system. But how do electrons decide which houses to move into? Well, it's not random at all. There are very specific rules that govern this whole arrangement.
The first, and maybe the most important rule, is the Pauli exclusion principle. And it sounds fancy, but it just means this. No two electrons in an atom can have the exact same set of 4 quantum numbers. Think back to our address. This is like saying you can't have 2 people with the exact same details at the exact same address. So since the first 3 numbers define the orbital, the house, it leads to a huge conclusion. Each orbital can hold a maximum of 2 electrons, and they have to have opposite spins. One has to be spin up, the other spin down.
Next up is Hund's rule. And you can think of this as the bus seat rule. You know how people on a bus will take an empty row before they sit next to someone? Electrons do the same thing. When they're filling up a subshell with multiple orbitals, like those 3p orbitals, they will each take an empty orbital first before they start pairing up. And all these single electrons will have the same spin, because that's the most stable arrangement.
And when you follow these rules, you get what we call an element's electronic configuration. It's like a shorthand for the address of every single electron. Take carbon. 1 is squared, 2s squared, 2p squared. That tells us it has 2 electrons in the first shell's s orbital, 2 in the second shell's s orbital, and 2 more spread out in the p orbitals. And this isn't just about keeping track of things. This system is the very foundation of the periodic table, and it explains pretty much all of chemical bonding.
So this entire address system describes what we call the ground state, the most stable, lowest energy arrangement of electrons in an atom. This knowledge is everything in chemistry, but it leaves us with one final, really interesting question. What does it take to actually change an electron's address? Well, the answer to that involves energy, light, and the very essence of what makes chemical reactions happen.